I'm going to be talking about affine invariant mid-range statistics, and this is going to be based again on symmetric positive definite matrices, so it's very much continuing the theme for the session so far. So just to start at the basics, the mid-range of a collection of real numbers is simply defined as the arithmetic average of the extreme values. And it turns out that this is the unique solution to the optimization problem of minimizing the maximum distance to the data points. And so one thing to note about the mid-range is that it's very sensitive to outliers, as one would expect, because it's defined using the extremes. But nonetheless, it can be a useful measure in some contexts. And in particular, it's an important notion in the statistics of extremes. One interesting thing to note is that it's the maximally efficient estimator for the center of a uniform distribution. So if you have a symmetric or uniform collection of points, the mid-range will actually be a pretty sensible notion for an average for the set. So you don't have to go through all of the data points, essentially. So in this talk, again, I'll be focusing on symmetric positive definite matrices, and we've seen, so I won't dwell on this because we've sort of established that they're very important in applications. Essentially, the reason is that covariance matrices are pretty ubiquitous in applications from computer vision to machine learning and so on, and they tend to have this, they do have this structure. So one simple example is diffusion tensor imaging, for instance, where you have a field of 3x3 covariance matrices that you want to sort of do processing on, do statistics on, and so on. But one can also have examples where the dimension of the covariance matrices are much larger. And one example of this would be something from brain-computer interface, or BCI technology, where essentially we end up with, we have an array of sensors and we construct covariance matrices from these signals, and we end up with a sort of time-varying SPD matrix valued data, and we'd like to do things like classification and dimension reduction and so on such a set of data. And these algorithms all require a notion of a relative distance and sort of interpolating curves between data points, and that's where the geometry naturally sort of comes in. SPD matrices are sort of points in a cone embedded in a linear space, so they have this natural Euclidean or sort of linear geometry that they inherit. But it's been noted in many works that, and it's pretty well understood now, that using nonlinear geometries that are related to generalized spectral properties of the matrices often yield significantly improved performance. So the space of SPD matrices of a given dimension forms the interior of a closed and convex cone in the linear space of symmetric matrices, and it also has this manifold structure. And as was noted before, a sort of key geometry associated with this space is the so-called affine invariant geometry, whereby essentially congruence transformations play the role of sort of translations in a linear space. So we can move around the space using congruence transformations. And indeed, the action by the general linear group is transitive, and it makes the space a homogeneous space, and so on. So then, often for analysis purposes, we would like to make sure that additional structures that we endow the space with, such as metrics, would also be invariant under these transformations. And there are very good practical reasons for wanting to do this, but I'll skip that. So the framework for this work is Finsler geometry. And so if you haven't come across Finsler geometry and Finsler metrics, if you think of a Riemannian metric as a sort of smoothly varying norm from point to point, you can think of a Finsler metric. So if a Riemannian metric is a smoothly varying inner product, a Finsler metric would be a smoothly varying norm. So where the norm doesn't have to come from an inner product. So it's sort of a generalization in that sense. And we get these family of affine invariant metric distances that are sort of derived from these local structures. And that's sort of the form on top of the slide there. And all we need is that this symmetric, phi has to be a symmetric gauge function on vectors. So essentially, as long as phi is invariant under permutations and sign changes of coordinates, then that generates this unitarily invariant norm on the eigenvalues, and then And the log there also introduces the nonlinearity in the metric. So as an example, if we take phi to be the gauge function corresponding to the LP norm, then we recover the Schatten P norms at the identity, and then we can extend that to the metrics on top. And P is equal to 2 just yields the standard affine invariant Riemannian metric that we've seen a few times. So a key point about the Riemannian metric is that if you have 2 points A and B, there will be a unique geodesic that connects A to B. And it turns out that this geodesic, this curve is a length minimizing geodesic for any of the affine invariant metrics introduced before. And this follows from this beautiful argument based on the metric increasing property of the exponential map on the cone of positive definite matrices. But I won't dwell on that too much. The question of uniqueness is important. So it turns out that if P is not equal to 1 or infinity, this sort of well-known Riemannian geodesic ends up being the unique geodesic for all of the Finsler norms for P not equal to 1 or infinity. When P is 1 or infinity, we could have other geodesics as well. And in particular, for P is infinity, which is sort of the focus of this talk, we obtain essentially as the Finsler metric distance, this Thompson metric on the cone of positive semi-definite matrices. And this metric, in general, admits infinitely many geodesics between a pair of SPD matrices. So one thing to note about this, the formula for the metric is that which has computational significance, is that it doesn't require the computation of the full generalized eigenspectrum of the pair AB. It only needs the extremal eigenpairs, eigenvalues. And there are very efficient, scalable, matrix-free algorithms for computing these, essentially power method-based sort of approaches. So given some kind of metric structure and geodesics, a natural way of coming up with an average, coming up with the notion of an average of 2 points is to take the metric midpoint as an average. So the midpoint of one geodesic that connects the 2 points. And indeed, the geometric mean, which is quite well known, corresponds precisely to the midpoint of the unique geodesic in the Riemannian case. So this sort of well-known mean comes through this sort of, has this interpretation. Now, among the infinite set of minimizing geodesics of the Thompson metric, there's this one that has this very nice form on the bottom there, and it has this sort of extra feature that in the case of 2x2 matrices, this coincides with the Riemannian geodesic. So even in 2x2, for 2x2 matrices, the Thompson metric has an infinite number of geodesics in general, but one of these with this nice expression only involving extremal eigenvalues happens to coincide with the Riemannian one in that case. So it's a very natural one to sort of stick to for now. And so one obvious question is, how does this matching between Riemannian and this cheaper Finsler geodesic sort of go up in dimensions? I won't go into this too much. So in 2 dimensions, there's a perfect match. In 3 dimensions, we see here with the row on the bottom that the match is actually quite good. And that's a sort of typical thing. It's almost surprisingly good because the Finsler geodesic there is only using 2 eigenvalues out of 3, whereas the Riemannian one is using 3. But you know, it's not 2/3 as good. It's pretty close, actually. Now, we've been looking very closely at how this scales up with n, and there's too much to go into, so I'll just skip all that for now. And this is just sort of a picture produced by one of our summer students of how sort of DTI with different types of interpolations work. The key point is the Riemannian and Finslerian are pretty close. Okay, so if we now plug in t is equal to half in the formula for the Finsler geodesic, we get this A star B mid-range. And again, the thing to note is that this formula now only involves the computation of extremal generalized eigenvalues, so it scales remarkably well compared to the geometric mean, and so it looks good, basically. Once we have a notion of some kind of a mapping that takes in 2 matrices and gives out something like an average, there's a number of sort of basic properties that any sensible notion of a measure of central tendency should probably satisfy, and here's 5 of them listed here. So we have continuity, symmetry, affine invariance, a sort of natural order property whereby if A is less than or equal to B, we want the average to fall in between, and also a monotonicity in the arguments. And it turns out that if we take the mu to be the star midrange, properties 1 to 4 hold in full, and then a weak form of 5 holds as well. And the weak form is that essentially it's sort of the extremal eigenvalues that stay monotone, so not the full matrix, not monotonicity in the full matrix sense. But that's a sort of a plausible result, I mean, given what we're using in the construction. So that looks sort of okay. Another interesting property is this geometric scaling property, that if we scale a matrix A and B by 2 sort of positive coefficients, the star midrange scales as the geometric mean of the coefficients. Now this is satisfied by the geometric mean, obviously, but it isn't satisfied typically for midranges. So this is another sort of special attribute of this particular choice. So the summary of the stuff so far on the star midrange, we've shown that it's a Thompson metric midpoint that is continuous, symmetric, and affine invariant, and has these nice sort of order and monotonicity properties. Okay, so now we move to the endpoint problem. So it's sort of instructive to go back to the scalar case. So if we have a bunch of positive real data points, scalars, the natural notion of the mid-range is obviously the geometric mean of the extremes in this case because of the multiplicative geometry of the ray. The optimization formulation is sort of the standard one that we had before essentially, and with some makeup. And then this extends to the vector mid-range problem in a very natural way. We just need to sort of replace the scalar norm with the infinity vector norm, the sort of supremum norm. And this expression in turn also has a natural extension to the matrix setting, where essentially we're using the d infinity metric in the cost function. So the endpoint midrange problem for matrices is given the endpoints yi, sort of minimize the maximum distance as measured by the Thompson metric to all the various data points. And any solution to this problem would be a midrange of the data. So we have these nice, so the cost function here is the maximum of the d infinity distances, and it has some kind of optimum t star, say, and we have these lower and upper bounds for what this optimum is. So I won't go into the upper bound, but the lower bound ends up being half of the diameter of the space of the data points as measured by the Thompson metric or d infinity metric. So we compute all the pairwise distances of the data points, and we take the maximum, and half of that is the lower bound. So in the vector midrange problem, again, we have the same setup. The lower bound is, again, the sort of natural thing you would expect, half of the diameter. And in this case, it turns out, as in the scalar case, that the lower bound is always attained. So at optimum, you always have, as your cost, half of the diameter. So that's good. So then we move to the matrix problem. So we have, again, the usual cost function. This isn't a terribly nice cost function for optimization. It's non-smooth because of the max and the norm. It's also not convex because of the logarithm and so on. But if through a sort of clever unraveling of this using an epigraph formulation, we can write it essentially as a quasi-convex problem. And that's sort of what we have on the bottom there. So this is quasi-convex because for any fixed t, all those feasibility constraints on the bottom, they're all just convex constraints. So you can solve them using standard convex optimization packages and SDB solvers and so on. So the way this would work is now you can use something called the bisection method to solve this problem. So you start with a t that's greater than the optimum, and you solve for x using whatever package you're using, and then you just gradually decrease t through whatever method. I mean, bisection is a standard one. So you have an upper bound, lower bound, and you keep taking sort of bisections. Now, crucially, if the lower bound is attained as in the vector case, then we don't even need to bother with this, because all we have to do is put L in for t and then solve for the feasibility constraints once. And then we have our mid-range, and that's the end of it. But unfortunately, and sort of remarkably, it turns out that the lower bound is not necessarily attained in the matrix case. And so this is one simple example for 3 2x2 matrices where if you work out half the diameter, it's less than the optimum cost as you would find using a quasi-convex program. Okay, yeah. So this sort of highlights that the problem is actually fundamentally different than the vector case. And this has to do with the fact that you can't sort of simultaneously diagonalize all the matrices and so on. So I don't know, do I have time for a few more minutes or 4 minutes? Oh. Okay, yeah, that's plenty of time. Okay, so now I have a few slides on visualizing the problem, the quasi-convex approach. So if you do it in the 2x2 case, you can visualize points in 3D. Each one of these feasibility constraints looks like the shape on the right. So you have one cone shooting up, as it were, and one cone negated shooting down. And they intersect in a shape like this. And so you'd have n of these if you have endpoints. And so what we want to do is, first of all, as we shrink t, these two vertices move closer together and the region shrinks along a straight line to nothing. And so if we look at the n is 2 problem, for instance, the problem is you have 2 of these regions and you keep shrinking t until there is no intersection. And eventually you find that for appropriate choice of t, these 2 regions touch on a line segment. And any point on that line segment will be a mid-range, and you get the right t. So the n is 2 problem has this nice interpretation. So yeah, that's pretty much what I was saying. So if we now look at the n is 3 problem, or higher than 2, these intersections can become pretty complicated for t. And as we shrink t, they don't sort of disentangle nicely. Sometimes you have a situation where only 2 of the feasibility sets sort of dominate and become active. And in those cases, the lower bound is attained. But generally, you have these complicated shapes, and the mid-range ends up being in a corner of something. So this is the plot for the 3 data points that didn't attain the lower bound. And so we get this sort of intersection that looks like the wing of a plane, appropriate for the setting, I guess. And then as you shrink t, it sort of ends up in a tight corner. And so it's fundamentally a more complicated problem, essentially. So if you did this problem for vectors, for instance, you'd have very nice parallel faces, and they would sort of untangle quite nicely, and you'd be done. Okay, so just to summarize, we've come up with a geometric matrix mid-range statistics framework based on optimization. We've looked at the n is 2 case sort of closely, and we've offered an algorithmic solution to the endpoint mid-range problem via quasi-convex optimization. This isn't very ideal for us because one of the motivations we had for the endpoint problem was that we wanted essentially something that scales much better than sort of like the Karcher mean or something. And these STP solvers, they don't do I mean, they're not terribly competitive. So ideally, we'd like an algorithm that's based purely on computing extremal eigenvalues, maybe a long sequence of them, but some kind of matrix-free algorithm. So that's one thing that we're working on. One other research project that we have ongoing is comparing how Finsler and Riemannian geodesics sort of compare in higher dimensions. It turns out that's a sort of rich and somewhat complicated question. So I think I'll wrap up there. So we have some work in the pipeline that we can sort of, if anyone's interested, I can discuss. But I'll be happy to take questions now. Thank you.